2020-2021, Part 4. My name is Gabriel Ebner, and in this video we're going to cover Chapter 11, Section 1, The Universe is in Lean. The beautiful thing about dependent type theory, the logic of Lean, is that most objects are terms, no matter whether we have a term like 1 plus 1, or a type like natural numbers, or a proposition like 1 equals 2, or a proof of, well, let's say 1 equals 1. All of these objects are just terms, and in Lean, all terms have types. So 1 plus 1 has the type natural number. Natural number has the type type, which means it is a type. 1 equals 2. Proposition, it also has a type, namely prop. And proofs have the proposition that they prove as their type, because propositions are also types. This uniformity of treating all these objects in the same way is very nice. For example, it means that we can use definitions to define both terms. We can have a definition that is a term. We can have exactly the same syntactic construct, a definition that defines a type. And we can have a definition that defines a proposition. So by treating all of those objects uniformly, we get a lot of nicety by being able to use things like definitions and other infrastructures such as design a texting framework. We can infer the types of every of those terms in the same and uniform way. So it's extremely nice that all of the objects in Lean are so uniform. Okay, so all of those are terms, and all of those have types. So if the natural numbers have type, then what about type? What type should type have? So one idea would be to say that type should have type, because it is a type. Okay? Unfortunately, this is a big problem. So if we said that type is a type, then we get so-called Shiraz Paradox, which falls exactly from type in type. This is a very complicated way to prove false, given the type theory in which we have type in type. So when we have type in a type theory, we can get false from this, which is bad because this means that the type theory is inconsistent. It means the logic is inconsistent, and we can prove everything, and hence we no longer have any guarantees about the theorems that we actually proved that they're actually true. So this is really, really bad. However, describing Shiraz Paradox is outside of the scope of this lecture. This would take way too long. A very related paradox is Russell's paradox. So all of those paradoxes in mathematical foundations, they come from about the beginning of the 20th century, when mathematicians first thought about the foundations of mathematics and tried to describe everything in nice formal ways. And people are very interested in doing this using set theory in mathematics. So many of those paradoxes are easily stated in set theory, and Russell's paradox is also a paradox about set theory. So just as in type theory, we cannot have the type is a type, is the type in type. We can also, in set theory, we have a very similar it's not a theorem, it's a paradox. So it's Russell's paradox. And the paradox is having a set of all sets that do not contain themselves. So you might have seen this in mathematics. So the idea is that we're in a set theory, everything is a set, and now when naively we might assume that we can write down a set of all sets that do not contain themselves. And this also leads to a contradiction. And this is much easier, which is why I want to show you the proof of how this leads to false. We just ask, is R an element of itself? And if we expand the definition of the right-hand R, then we see that this is that R in the set of all X which contain themselves, which then by definition should be something like R not an element of R. And if you have for any proposition that the proposition is true if and only if its negation is true, then we can derive false from it. Which means that once we have this, we can derive false. Think, for example, if R is an R, then this side is true and this side is false, and it's true if and only if false is false. And similar for in the other case. If R not in R is true, then R in R is false, and we have false if and only if true, which is also false. So both of those axioms are, both of those paradoxes say a bit about what we cannot do when we want to make a consistent foundation for our logic, for our proof assistant. And we can avoid those kind of paradoxes by restricting the way types can be formed. In set theory, it means that we want to have fewer sets. And in type theory, we solve this by having not type in type, but by considering a sequence of types. And this looks like this. Instead of saying that type is in type, instead we say that type 0 is in type 1, and type 1 is in type 2, and type 2 is in type 3, and so forth. This complicates the theory a bit, but it guarantees consistency. We can no longer derive false, which would be bad. Okay, so in a schematic form, if you want to look at a typing judgment for the sort, this means that a sort U has the type sort U plus 1. Okay, maybe I should explain the syntax here. So in Lean, we have type, which is the same as type 0. And then a prop is sort 0. If I draw this here on the screen, so we have that prop is a type, has type, and type has type 1, and type 1 has type 2 as type, and so forth. And prop is just sort 0, so that we can talk about prop and type generically. So type is the same as type 0, which is the same as sort 1. And type 1 is sort 2. And type 2 is sort 3. in this way we can talk generically about both the prop universe and the type universe. The number after the sort or type is called the universe level. So the 0, the 1, and the 2 and the 3, these are called universe levels. And we can also have universe levels that are not numbers, but that are instead letters, which allows us to talk generically about a definition that works for all universes. So if we can also, so the legal syntax for this is we have already seen prop and type. Prop is in type is in type 1, type 1 is in type 2, and so forth. And if we write this using sort, lean will always pretty print this as proper type. So sort 0 is pretty printed as prop, and sort 1 is pretty printed as type. Sort 2 is then pretty printed as type 1. So under the hood, lean doesn't know the difference between type 1 or sort 2. It's represented exactly the same way. This is just syntactic sugar on top. And if we want to talk about universe variables, so if we want to have a universe level that is not a fixed number, then we write, we need to declare the universe variables first. So we need to say universe variables uv, and then we can use them where we would otherwise use a universe level number. So we have here check type u, and we see that type u is in type u plus 1. And we can, of course, do the same also with sort. And we can also do a little bit of addition here. So we can say sort u plus 3, which is then pretty printed as type u plus 2. And so you can also do u plus 3 plus 5, but it's very limited, so you cannot do this. You cannot say 5 plus u. And since it's sometimes a bit not very convenient to write sort u all the time, in particular if you want to talk about multiple universes, you'd then have like type u, type v, type w, and then maybe you need to do type u1, type u2. So you quickly run out of indices sometimes. Therefore, lean can, in some cases, find the most general universe that works. And for this, you write type star. So what happens then is that lean will insert some universe level that it thinks is the most general one. So if you just write down type star, it will put in some universe level. For example, if we do check type star equals type u plus 10, then it will pick again the most general universe level that will work, which in this case is u plus 10, even though we put a star here. But think of star as just an easy way to pick the best universe possible. Important thing is that typically we want to write definitions that are as universe polymorphic as possible. So universe polymorphic means that the definition works not just in one universe, but in several universes. If you think about the identity function, you might want to define this as the function ID, which takes an argument, which takes a type as first argument, and then an element of this type, and returns this type. Okay, so we can apply this to any term. However, this function is not universe polymorphic, which means that you cannot use it for types, for example. So you can only apply it to terms whose type is in type 0, but not types whose type are in higher universes. You can also, right? And this is the reason why we typically want to use type star here, because then it also works in other universes. If you look at this, if you look at what lean actually produces, lean inserts a u_1 for the star here. Okay, so right, the takeaway is we always want to define things as generically as possible so that we can use it in more places. So, and maybe another one. So, but it's still not generically enough. So we can't apply it to proofs yet. This is because we have type here, and we should actually be using sort. So it is good practice to write your definitions whenever you have like a type variable in your definitions. For example, you define lists, or if you define like functions on lists or functions that are polymorphic in the type, you should always define them using type star or sort star.